All right, I want to talk to you about acceleration versus time graphs, because as far as motion graphs go, these are probably the hardest. One reason is because acceleration just naturally is an abstract concept for a lot of people to deal with, and now it's a graph, and people don't like graphs either, particularly oftentimes. And another reason is if you wanted to know the motion of the object, let's say it was this doggy, this is my doggy Daisy. Let's say Daisy was accelerating. If you wanted to know the velocity that Daisy had, you can't figure it out directly from this graph unless you have some extra information. You'd have to know information about the velocity Daisy had at some moment in order to figure out from this graph the velocity Daisy had at some other moment. So what can this graph tell you about the motion of Daisy? Well, let's say this graph describes Daisy's acceleration. So Daisy's going to be accelerating. Maybe we're playing catch. We'll give her a ball. We'll throw the ball. Hopefully she actually lets go when she brings it back. And this graph's going to represent her acceleration. So this graph, if we just read it, it says that Daisy had 2 meters per second squared of acceleration for the first 4 seconds. And then her acceleration dropped to 0 at 6 seconds. And then her acceleration became negative until it was -3 at 9 seconds. But from this, we can't tell if she's speeding up or slowing down. What can we figure out? Well, we can figure out some stuff because acceleration is related to velocity. And we can figure out how it's related to velocity by remembering that it is defined to be the change in the velocity over the change in time. So this is how we make our link to velocity. So if we solve this for delta v, we'd get that the delta v, the change in velocity over some time interval, will be the acceleration during that time interval times the time interval itself, how long did that take. And this is the key to relating this graph to velocity. So in other words, let's consider this first 4 seconds. So between 0 and 4 seconds, Daisy had an acceleration of 2 meters per second squared. So that means, well, 2 was the acceleration meters per second squared times the time was 4 seconds. So there was 4 seconds worth of acceleration. And you get +8. And what are the units? This second cancels with that second. You get +8 meters per second. So the change in velocity for the first 4 seconds was +8. This isn't the velocity, it's the change in velocity. How would you ever find that for this diagonal region? This is a problem. Look at this. If I wanted to find, say, the velocity at 6 seconds, well, the acceleration at this point is 2, but then the acceleration at this point is 1, and the acceleration at this point is 0. That acceleration would keep changing. How would I ever figure this out? Like, what acceleration would I plug in during this portion? But we're in luck. This formula allows us to say something really important. A geometric aspect of these graphs that is going to make our life easier. And the way it makes our life easier is that, look at what this is. This is saying acceleration times delta t. But look at, the acceleration we plugged in was this, 2. So for the first 4 seconds, the acceleration was 2. The time, delta t, was 4. We took this 2 multiplied by that 4 and got a number, +8. But this is a height times a width. If you take height times width, that just represents the area of a rectangle. So all we found was the area of this rectangle. The area is giving us our delta v because area, right, of a rectangle is height times width. We know that the height is going to represent the acceleration here, and the width is going to represent delta t. And just by the definition of acceleration rearranged, we know that a times delta t has to just be the change in velocity. So area and change in velocity are representing the exact same thing on this graph. Area is the change in velocity. And that's going to be really useful because when you come over to here, the area is still going to be the change in velocity. And that's useful because I know how to easily find the area of a triangle. The area of a triangle is just 1/2 base times height. I don't easily know how to deal with an acceleration that's varying within this formula, but I do know how to find the area. For instance, the area here, though I have 1/2, the base is 2 seconds. The height is going to be +2 meters per second squared. And what are we going to get? One of the halves cancel, well, the half cancels with one of the 2's, and I'm going to get that this is going to be equal to 2. meters per second, that's going to be the area. That represents the change in velocity. So Daisy's velocity changed by 2 meters per second during this time. Now you might object. You might say, wait a minute. I'll buy this over here because height times width is just a times delta t. But triangles, that has an extra factor of a half in it, and there's no half up here. How does this, how can we still make this claim? And we can make this claim because we'll do the same thing we always do. We can imagine, all right, imagine a rectangle here. We're going to estimate the area with a bunch of rectangles. And then this rectangle, and then this rectangle, and you're like, that looks horrible. That doesn't look like the area of a triangle at all. It's got all these extra pieces right here, right? You don't want all of that. And okay, I agree. That didn't work so well. Let's make them even smaller, right? Smaller width. So we'll do a rectangle like that. Then we'll do this one. And you see we're getting better. Like, this is definitely closer. This is not as bad as that other one, but it's still not exact. And I agree, that is not exact. So we'll make it even smaller rectangle and then an even smaller rectangle here. All these are the same width, but they're even smaller than the ones before. Now we're getting really close. This area is really going to get close to the area of the triangle. And the point is, if you make them infinitesimally small, they'll exactly represent the area of the triangle. And each one of them can be found with this formula. And the delta V for each one will be the acceleration of the height of that rectangle times the small infinitesimal width, and you'll get the total delta V, which is still going to be the total area. Long story short, area on a acceleration versus time graph represents the change in velocity. This is one you got to remember. This is the most important aspect of an acceleration graph, oftentimes the most useful aspect of it, the way you will analyze it. So why do we care about change in velocity? Because it'll allow us to find the velocity. We just need to know the velocity at one point, and then we can find the velocity at any other point. For instance, let's say I gave you the velocity Daisy had. For some reason, I've got a stopwatch. I start my stopwatch, and right at that moment, at t equals 0, Daisy had a velocity of, let's say, positive 1 meter per second. So Daisy was traveling that fast at t equals 0. That was her velocity at t equals 0 seconds. Now I can get the velocity wherever I want. If I want the velocity at 4, let's figure this out. To get the velocity at 4, I can say that the delta V during this time period right here, this 4 seconds, I know what that delta V was. That delta V was positive 8. We found that area, height times width. So positive 8 is what the delta V's got to equal. And what's delta V? That's V at 4 seconds minus V at 0 seconds. That's got to be positive 8. I know what V at 0 seconds was. That was 1. So I can get that V at 4 minus 1 meter per second is equal to positive 8 meters per second. And so I get the velocity at 4 was positive 9 meters per second. And you're like, whew, that was hard. I don't want to do that every time. Yeah, I wouldn't want to do that every time either, so there's a quicker way to do it. We can just do this. What's the velocity we had to start with? That was 1. What was our change in velocity? That was positive 8. So what's our final velocity? Well, 1 plus 8 gives us our final velocity is positive 9. We're always just going to take this change in velocity, this area, which represents the change in velocity, we're just going to add our initial velocity to it when we solve for this final velocity. For instance, if that didn't make sense, for instance, if we want to find the velocity at 6, well, we can just say we started at t equals 4 seconds with a velocity of positive 9. We started here with positive 9. Our change was positive 2, so we're going to end with positive 11 meters per second. And you might object. You might say, wait a minute. Hold on now. If we want delta V, right, and that's positive 2, shouldn't delta V be the whole thing from like 0 to 6 seconds? Shouldn't I say V at 6 seconds minus V at 0 is positive 2 meters per second? And I can't do that. And the reason I can't do that is because look at what I did. On the left-hand side, my time interval goes from 0 to 6. But on the right-hand side, I only included the area from 4 to 6. That's the area, this yellow triangle right here. If I wanted to put 6 and 0 on this left-hand side, I could do that. But for my total area, I wouldn't use that. I'd have to use the total area. In other words, the total area from 0 all the way to 6, because that's what I defined on this side. These sides have to agree with each other. So from 0 to 6, my total area would be, this area here was 8, right? We found that rectangle was 8. This area here was 2. So my total area would be 10. I can do that if I want, and then I could say v at 6 minus v at 0 was, well, v at 0 we said was 1, because I just gave you that, equals 10 meters per second, and I get that the v at 6 would be 11 meters per second, just like we got it before. So you can still do it mathematically like this, but make sure your time intervals agree on both sides. Now let's do the last part here. So we can find this area, and the area always represents the area from the curve to the horizontal axis. So in this case, it's below the horizontal axis. That means it's going to be negative area, and the reason is it's a triangle again. So 1/2 base times height. So 1/2, the base is 1, 2, 3 seconds. The height is -3. Negative now, -3 meters per second squared. I get that the total area is going to be -4.5 meters per second. All right, now Daisy's going to have a change of velocity of -4.5. If we wanted to get the velocity at 9, there's a few ways we can do it, right? Just conceptually, we could say that Daisy started at 6 with a velocity of 11. Her change during this period was -4.5. So if you just add the two, you add the change to the value she started with, well, you're going to get positive 6.5 if I add 11 and -4.5 meters per second. Or if that sounded like mathematical witchcraft, you can say that, all right, delta V equals what? -4.5 meters per second. Delta V would be, all right, you got to be careful. This -4.5 represents this triangle, so it's got to be the delta V between 6 and 9. So V at 9 minus V at 6 has to be -4.5 meters per second. V at 9 minus the V at 6 we know. V at 6 was 11. So I've got -11 meters per second equals -4.5. Whoa, running out of room. V at 9 would be -4.5 plus 11. That's what we did up here. We got that it was just 6.5 meters per second, and that agrees with what we said earlier. So finding the area can get you the change in velocity, and then knowing the velocity at one moment in time can get you the velocity at any other moment in time. Just be careful. Make sure you're associating the right time interval on both the left and right side. They have to agree. One more thing before you go. The slope on these graphs often represents something meaningful, and that's the same in this graph. So the slope of this graph, let's try to interpret what this means. The slope on an acceleration versus time graph, well, the slope is always represented as the rise over the run. And the rise is y2 minus y1 over x2 minus x1, except instead of y and x, we have a and t. So we're going to have a2 minus a1 over t2 minus t1. This is going to be delta a, the change in a over the change in time. What is that? It's the rate of change of the acceleration. That is even one more layer removed from what we're used to dealing with, right? Velocity is the change in position with respect to time. Acceleration is the change in velocity with respect to time. And now we're saying that the something is the change in acceleration with respect to time. What is it? It's the jerk. So this is often called the jerk. That's the name of it. It's not used all that often. It's quite honestly not the most useful motion variable you'll ever meet, and you won't get asked for it all that often, most likely on tests and whatnot, but it has its applications sometimes, and it exists, and it has a name. It's called the jerk. So recapping, the area, the important fact here is that the area under an acceleration versus time graph gives you the change in the velocity, and once you know the velocity at one point, you can find the velocity at any other point. And the slope of an acceleration versus time graph gives you the jerk.